Hello again, I'm Dr. Samuel Alexander, mathematician and philosopher, still here. I was thinking about how to do the figures for this proof, and it occurred to me that there might be an easier way to do the proof of this main theorem in this Knight-Darwin law paper. I'm writing this Knight-Darwin law paper. It's a paper about how a certain law that was proposed by Charles Darwin in his Origin of Species, which was not proven there, it was extrapolated from observations. I'm arguing that it's actually in fact a provable theorem from an assumption which I call the identical ancestor point axiom. I introduced this axiom in my paper Species-like Clusters based on Identical Ancestor Points, published this year in the Journal of Math Biology, and a couple other assumptions. And in the last stream, I had started working on figures, and since then I've been thinking about the figures for the proof of the main theorem, and in thinking about them, I got an idea of maybe an easier way to do this theorem. We'll start with the same paragraph as before. Suppose that big U equals U1, U2, dot 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 is an infinite directed path in S. We must show some UI has multiple parents. That big V equals V1, V2, dot dot dot, and big W equals W1, W2, dot dot dot, be two infinite directed paths in S, as in the definition of competition trivial. So Vi not equal to Wj for all ij. Now I'm going to split into cases as before, but not the same cases. I'm going to say case 1 is that both big V backslash big U and big W backslash big U are finite. In that case, by discarding initial segments of big V and big W if needed, we may assume that big V is a subset of U and big W is a subset of U. Assume that, let's see, how do I want to say this? Assume that an element of, well, let's say, assume that the smallest I such that UI is in big V, is smaller than the smallest j such that uj is in big W. The opposite case is similar. Let K be maximal such that rather, let me say, let I be minimal such that UI in V, and let J be minimal such that UI in W, such that Uj in W. In big W, we may assume that I is less than J. Actually, we don't even need to make that assumption. We don't even need the J at all. Let I be minimal such that UI is in big V. Let J be maximal such that let j bigger than I be maximal such that the set ui plus 1 dot 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 uj contains no element of big W. And in parentheses I'll say there must be some such j, since big W is a subset of U and big W is infinite. No, this is not what we want. Rather, let j bigger than I be maximal such that the set ui plus 1 dot dot dots uj is a subset of big V. And there must be some such j, since big W subset U, big W is infinite, and big W intersect big V is empty. Let's say by discarding initial segments of big V and W and relabeling, if needed, we may assume big V subset big U and big W subset big U. Say uj equals vk. Now the choice of j, we must have vk plus 1 equals u l for some l bigger than j plus 1. Thus, ul has parents u sub l minus 1 and v sub k or rather, let's say thus the two parents ul, thus the two parents ul minus 1 and v sub k of v sub k plus 1 are distinct. As desired. Yeah. And as I remarked previously, this is kind of the silly edge case. Like, this is the degenerate edge case, and yet it's the hard case. Now, case 2 is that let me rewrite case 1. Case 1 is, well, no, let me not do that. Case 2 is that big V backslash big U is infinite, or big W backslash big U is infinite. By symmetry, assume big V backslash big U is infinite, semicolon, the other case is similar. Since, by the assumption atop section prelim section U sub 1 has only finitely many ancestors, thus there is some I such that Vi is not an ancestor. Thus there is some I, thus there is some V sub I in big V backslash big U such that V sub I is not an ancestor of U sub 1. Now we're basically repeating the proof from the proposition of the weak version of the main theorem. And in fact, I think this is going to simplify the proof of the main theorem so much. I'll just delete that proposition, the weak proposition. Thus there is some Vi in big V backslash big U such that Vi is not an ancestor of U1. Since Vi has infinitely many descendants in S, namely Vi plus 1, Vi plus 2, ... And since the set U2, U3, ... is an infinite subset of S, the IAP axiom guarantees that Vi has some descendant Uj with j bigger than or equal to 2. Thus, there is a finite directed path x1 ... xk in G with x1 equals Vi and xk equals Uj by the convexity axiom. By the convexity axiom, x1 ... xk is a subset of S. Well, actually, let me delay invoking the convexity axiom for grammatical reasons. Let L be minimal such that XL is in big U. So L must be bigger than 1. Well, rather I'll say since Vi is in big V backslash big U, this forces L bigger than 1. by the convexity axiom, x sub L minus 1 is in S. It has ancestor x1 in S and descendant xl in S. Say x sub L equals u sub, I'm running out of letters here. Wait, I don't think we actually need that j is bigger than or equal to 2. I don't think we need to refer to j here. Let's see. And since big U is an infinite subset of S, the IAP axiom guarantees the I has some descendant U sub j. Well, what we can do is we can say some descendant U sub j in big U, parentheses, we may choose j minimal. Well, we may choose j as small as possible. Then we'll say, thus there is a finite directed path x1 dot dot xk and g with x1 equals vi and xk equals uj by choice of j, by minimality of j. Well, we must have j bigger than 1 because because otherwise vi would be an ancestor of u1, parentheses contrary to choice of vi. By minimality of j, we have x sub k minus 1 is not in big U. Thus, well, actually, let's put that first. We say by minimality of j, we have wait. Vi has some descendant to j in big U. We may choose j as small as possible. we must have j bigger than 1, because otherwise vi would be an ancestor of u1, contrary to choice of vi. By minimality of j, we must have that x sub k minus 1 is not in big U. Parenthesis. By minimality of j, we have xk minus 1 not in big U. Parentheses, if xk minus 1 were in big U, then since g is a DAG, xk minus 1 would equal u sub l for some l less j, contradicting minimality of j. But x sub k equals u sub j. Thus, u sub j has, thus, the parents u sub j minus 1 and x sub k minus 1 of u sub j must be distinct. By convexity, x sub k minus 1 is in big S. It has ancestor x sub 1 in big S and descendant x sub k in big S. Thus, u sub j has multiple parents in big S as desired. QED. Yeah, that's a drastic simplification of that proof. Rather than delete the previous proof, I'm just going to comment it out for the time being. And that's so much simpler that I think we no longer even need the proposition. I'm just going to comment out the figure from the proposition, but delete the whole proposition itself. And then up above, delete the paragraph where we say we know state of weak version, etc. There's a huge paragraph which is vestigial. Let's delete that vestigial paragraph. We're left with lemma for any S subset GFS is competition trivial. Yeah. Now we need a blurb to introduce the theorem. We now state the main theorem of the paper, which elevates a version of the Knight-Darwin law to the status of provable theorem. Of provable result. Provable theorem. We now state the main result of the paper, which elevates a version of the Knight-Darwin law to the status of provable theorem. Right. Let's compile. I like that. That's a significant improvement. A significant simplification. Let me proofread this new proof. Theorem. Let S subset G and assume S satisfies the convexity axiom, S satisfies the IAP axiom, S is not competition trivial, then S satisfies the Knight-Darwin law. Proof. Suppose big U equals U1, U2, dot 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 is an infinite directed path in S. We must show some UI has multiple parents. Let big V equals V1, V2, dot dot dot, and big W equals W1, W2, dot 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 be two infinite directed paths in S. As a definition vor, so Vi not equal to Wj for all ij. Let me simplify that condition. So big V intersect big W equals empty set. Recompile. Case 1. Both big V backslash big U and big W backslash big U are finite. By discarding initial segments of big V and big W and relabeling if needed, we may assume big V subset big W. We may assume big V subset big U and big W subset big U. Let I be minimal, such that UI in big V. Let j bigger than I be maximal, such that this at UI plus 1 dot 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 uj is a subset of big V. There must be some such j, since big W subset big U, big W is infinite, and big W intersect big V is empty. Say uj equals vk. By choice of j, we have vk plus 1 equals ul for some l bigger than j plus 1. Thus the two parents ul minus 1 and vk of vk plus 1. Let me reword that to be a little less grammatically confusing. Thus vk has two distinct parents in S, namely u sub l minus 1 and v sub k as desired. Recompile. Case 2. Big V backslash big U is infinite, or big W backslash big U is infinite. By symmetry, assume big V backslash big U is infinite. The other case is similar. By the assumption, adopt section 3. U1 has only finitely many ancestors. Thus, there is some UI in big V backslash big U, such that Vi is not an ancestor of U1. Since Vi has infinitely many descendants in S, namely Vi plus 1, Vi plus 2, dot dot dot, and since big U is an infinite subset of S, the IAP axiom guarantees that Vi has some descendant Uj in big U. We may choose J as small as possible. Thus, there is a finite directed path x1 dot 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 xk in big G, with x1 equals Vi and xk equals Uj. We must have J bigger than 1. Because otherwise Vi would be an ancestor of U1, contrary to choice of Vi. By minimality of J, we have xk minus 1 not in big U. If xk minus 1 were in big U, then since G is a DAG, xk minus 1 would equal ul for some l less j, contradicting minimality of J. Well, technically xk minus 1 could be technically k could be equal to 2. contradicting minimality of j, parentheses if k bigger than 2, or contradicting v x, contradicting v I not ambiguous if k equals 2. If xk minus 1 were ambiguous, then since j is a DAG, xk minus 1 would equal ul for some l less j, contradicting minimality of j if k bigger than 2, or contradicting vi not ambiguous if k equals 2. Thus the parents uj minus 1 and xk minus 1 of uj must be distinct. By convexity, xk minus 1 is an S. It has ancestor x1 and S, and descendant singular. Xk and S recompile. It has ancestor x1 and S and descendant xk and S. Thus, uj has multiple parents in S as desired. Nice. Git commit. Git commit. Drastically simplify proof of main theorem. Okay. Now I might have to do something shortly here, so I'm going to call it a day for now. I'm Dr. Samuel Allen Alexander. Please like, comment, and subscribe. I'll see you in the next video.